Hello. We start our 22nd lecture. So, section 22.1, higher order derivatives. So, definition is by induction. If there exists derivative of the order n minus 1 on an open set let's say G, and there exists the derivative at a point x naught in G, then it is called nth derivative and the notation is nth derivative at x naught equals to derivative of the order n minus 1 at x naught. The sound volume decreased. What happened? Did you see it's okay now? Okay. So, and you see notation also is here, and how to read that notation. So we start, let's say, n equals to 2, right? So the derivative f2 minus 1 is just the first derivative. It's another notation, nothing else. Nothing else. And to make everything in the same scheme, we can also put zeroth order derivative. It's by definition the function itself, nothing else. So, first derivative, new notation for the first derivative, new notation for the function itself, to put everything in the same scale of derivatives. And so you see, for n equals to 2, we talk about second order derivative. What is it? So it's by definition is derivative of the first order derivative. So once the function is differentiable on an open set, and we can discuss then the derivative of the derivative, and the derivative of the derivative is called second derivative. And we can continue further. There is one more notation. So we can denote it also by dnf over dxn. at x naught. But what appears here is called differential, but it is not included into your lecture notes, so we'll not talk about the formal sense of this notation yet. Okay, so let us consider one example, how it is called in your lecture notes, but I would say this is a theorem. So theorem 1, Leibniz rule. Oh, Leibniz formula. Leibniz formula. Okay, maybe formula is better, because Leibniz rule has a different meaning. Okay, without it. Leibniz formula. So if f and g have derivatives of orders 1, 2, so on up to n, let's say at x naught, then the product f times g also has nth derivative at x naught, and the following formula is true, and derivative is equal to sum k from 0 to n. Okay, once again, there is a choice for notations, so maybe I'll indicate here both and k. Or it's another notation for the same thing. And you see that the formula is very similar to Newton's formula, and in fact it is proved in a very similar manner. So proof by induction. By induction. So we start with n equals to 1. First step, n equals to 1. Here, what we need to check. Okay, I'll use what is used in your lecture notes here. Okay, so that is what we need to check. And you see that in fact it's nothing else but usual formula for the derivative of the product, because you see we have fg prime at x naught equals to, the sum contains two terms, c1 0 f0 g 1 at x naught plus c1 1 f1 g0, and recall notations for zeroth derivative as the function itself, and c1 0, c1 1 equal, both are equal to 1. So we have f at x naught g prime at x naught plus f prime at x naught g at x naught. And that is nothing else but the rule to find the derivative. And now the main step, second step. So we start with the induction hypothesis. So what is it here? Induction hypothesis. N equals to m, let's say. And it means that we suppose m's derivative at arbitrary point can be found using the formula, the Leibniz formula. And since the point is arbitrary, I'll use here arbitrary point. Instead of x naught, it's better to write just arbitrary point x. So after that, we suppose it's true, and we need to check n equals to m plus 1. That is what we want to prove. So m plus 1 at a point x naught equals 2. That is a question. Sum k from 0 to m plus 1, c m plus 1 k, f k, g m plus 1 minus k, and that is what we need to prove. How to proceed? So we know that by the definition of the derivative, so m plus 1th derivative is equal to, by the definition, as derivative of mth derivative. And for mth derivative, we have induction hypothesis, so we can substitute. And I'll omit argument in the functions here, derivative at the point x naught. So we have derivative of a sum which is equal to the sum of derivatives. So finitely many we proved for 2 terms, hence it is valid for finitely many terms as well. And then we have derivative of product, and we know the rule to find derivative of the product. So we need to find derivative of the first term, and that is, by the definition, the k plus 1 derivative times second term plus first term times derivative of the second, m minus k plus 1 then. That is according to the rule to find the derivative of a sum. Now we'll proceed similarly to Newton's formula. So we split the sum into the sum of two types of terms, the first terms and the second terms, and we split them into two sums. And also I'll do the following thing. So for the first sum, I'll separate that sum into different terms, the sum of the first m terms plus the last. So let me write down what we obtain then. Plus the very last term with k equals to m, that is this one, for k equals to m. That is the sum of the first terms. Now we do similar thing with the sum of second terms, but here again I'll split. So better to say, I would like to separate just one term. Now which term I want to separate? The very first with k equals to 0. So it means the main body contains terms k from 1 up to m, c, m, k, f, k at x naught, g, m minus k plus 1 at x naught, plus the first term with k equals to 0, and that is c m0, f 0, x naught, g m minus 0 plus 1 and x naught. Okay. Okay. So we continue then. Now let us unify the main bodies. So the first sum and the third term of this sum, which is again a sum of m terms. But for the first sum, let me change here the summation index. So put j equals to k plus 1, or it means k is j minus 1. Then the first sum will be sum j from, now j starts from 1 up to m, c m j minus 1, f, so k plus 1 now is j, x naught, g And here m minus k will be m minus j plus 1. M minus j plus 1 takes no. That is the first sum. Next, CMM. What is CMM? Let me recall. So CMM, m factorial, m minus m factorial. 0 factorial is 1, so we have 1. Hence, I can rewrite the second term as the derivative m plus 1th, m plus 1 order. Here derivative of order 0. It's the function itself, but for me it's better to preserve the notation like it is. And next main body will be the same. I'll not change it, maybe with one exclusion. Instead of k, I prefer to write sum again, j from 1 to m. So it means for this sum, I'll just replace the index of summation k by j, nothing else. So fj at x naught, g m minus j plus 1 at x naught, plus the very last term, cm0 is again 1, so f0 x naught, g m plus 1 and x naught. Now, I'll use the following property. Cmj minus 1 plus cmj equals to cm plus 1j. We proved that property while we considered Newton's formula. It's the same. Or maybe I used that notation, doesn't matter. So, using that formula, we can unify the first and the third into one formula, Cm plus 1j, fj at x naught, g m minus j plus 1. Okay, maybe I'll write m plus 1 minus j at x naught. But then what we can also observe, look, the very last term, here we have 1, but 1 equals to c m plus 1, 0. So it means the very last term is nothing else but the term with j equals to 0 here. And the second term, analogously, 1 equals to c m plus 1, m plus 1. And it gives j equals to m plus 1, substitute, and we have precisely the second term, so m plus 1 here. Now we collect all terms, and moreover we observe that this is precisely what we wanted to prove. So the formula is proved. Theorem is proved. Okay, maybe I would like to give more examples. So let us write a formula for nth derivative of sine and cosine. So, proof for those formulas. I'll consider only the first one. So here, how we can proceed? So n equals to 0, sine x 0th derivative is equal to sine x plus 0 times pi over 2. It's correct because of notations. 0th derivative of sine is the function itself, and here we have sine x as well. N equals to 1, sine x first derivative, it's cosine x as we know, and that is nothing else but sine x plus pi over 2 by trigonometric formulas. So again it's correct. N equals to 2, sine x second derivative is the derivative of cosine by the definition, that is minus sine x, and it is equal to sine x plus pi, or again by trigonometric formulas, or sine x plus 2 times pi over 2. That's it. N equals to 3, sine x third derivative is the derivative of second derivative, so the derivative of minus sine. The derivative of minus sine is minus cosine x, and we can replace it by sine x plus 3 times pi over 2, again by formulas, by trigonometric formulas. And what's after? Fourth derivative will give back sine x fourth derivative is derivative of minus cosine. It gives the function sine x itself, and you see that is precisely because of 2 pi periodicity of sine x plus 4 times pi over 2. And after that, the process will be repeated again and again. And because now we come back to the original function sine x. So then all derivatives will be repeated, and analogously all right-hand sides will be repeated as well. For cosine, it's quite analogous. Okay, that's it. Now, next section, very short one. So now next section. (22.2). It is called derivatives of parametric functions. Although that is not precisely correct. Why? Because, for example, what are parametric functions? What is most typical example? That is most typical example of parametric function, although this is not a function, rigorously speaking, because what is it? If t changes and t represent this angle, then we start from r here and we proceed along a circle of radius r. So the graph of this function is this circle, which is not a function, right? Because for one value x here, it corresponds to values of y, right? So this is not a function in the sense of the definition of a function. But traditionally, it is called parametric functions. That is quite usual. So, what is in general? In general, we have x of t, y of t. T varies, let's say, from a to b. And that is a general parametric function. And it gives y of x, in which case it gives a function. It gives a function if x of t is strictly monotone. If x of t is strictly monotone, then we can find an inverse. T of x is x minus 1, right? X minus 1, t of x. And then, if we substitute, instead of t, we have y of x, y of we substitute t of x, right? And it gives, in such a way, it gives a function of x, and we can find the derivative by chain rule. So dy over dx, here it's quite useful to use this notation, is equal to, so in general, we should write y prime at t of x times t prime at x. And what is it? Y derivative is with respect to t, let me indicate here, and t prime by the inverse function is equal to, so I may rewrite like that, x prime at t. And if we forget about this argument x, we can write down the formula like that. Or it's very nice to use the notation dy over dx. So here we have dy over dt over dx over dt. So it means that we can proceed in a formal way, right? So dy over dx equals to, we insert dt, and we have formal ratio of two ratios, and dt is cancelled, right? So you see that using that notation is very suitable just for parametric functions because of this cancelling of dt. And that is a rule to compute. So, couple of examples. Example 1. Find the derivative of the parametric function x equals to t squared and y equals to t cubed. In fact, here, this is not again a function, rigorously speaking. Why? Because we can represent one value of x using two different values of t, plus and minus. So, two different values of t plus and minus give us the same x, but plus and minus t give us two different values of y. So, it means for arbitrary value of x, for arbitrary positive value of x, we put into correspondence two values of y, plus and minus. That's it. So, nevertheless, we can proceed formally. So, dy over dx equals to dy over dt over dx over dt. That's it. 3t squared over 2t, and it gives 3 over 2t. So it means that the derivative of the parametric function is again a parametric function. What it means? We have x equals to t squared and dy over dx equals to 3 over 2t. So once again, we have parametric function. So derivative of the parametric function is again a parametric function. Example 2. Okay, same question. X e power 2t, y e power 3t. Here we have an inverse function, so no problem with two values. And dy over dx equals to dy over dt over dx over dt. That's it. E to the power 3t times 3t prime. Let me put here t. We take derivative with respect to t. So by chain rule. And it gives 3 over 2 e to the power t. That's it. Okay, let's have a break. So we continue. And now, as we observed, the derivative of parametric function is again a parametric function, and we consider second order derivative, and here so we can use either d2y over dx twice, or what's another notation, y double prime x twice. So to indicate that we differentiate with respect to x, we create the following notation. So what is in general then? We know what is derivative dy over dx, so it means that how we proceed. So dy over dx twice is the derivative of the first derivative. Dy over dx we computed before, so it means we have to find the derivative of the following ratio. With respect to x, and to find parametric derivative, what we need to do? We need to find the derivative with respect to t and to divide by dx over dt. So what it gives, let us rewrite derivative of the numerator times denominator minus derivative numerator times derivative of denominator over x prime over t squared over x prime over t, and it gives y double prime of t twice x prime t minus y prime t x double prime t twice over x prime with respect to t cube. That is how to compute the second order derivative, and one example to that topic. So example 3 then. Okay, there is no question here, so find the second derivative. Of y equals to f of x, x of t is t minus sine t, y of t is 1 minus cosine t, t from 0 to 2 pi. That is so-called cycloid. So, we solution proceed firstly by finding the first derivative, so dy over dx y prime over t over x prime over t, that's it, sine t over 1 minus cosine t, that's it. And then the second derivative, we need to find the derivative of the first derivative with respect to t and to divide by x prime of t, that's it, cosine t times 1 minus cosine t minus sine t times sine t over 1 minus cosine t squared, 1 minus cosine t, and it gives so cosine t minus 1 cosine squared and sine squared over 1 minus cosine t cube, or finally minus 1 over 1 minus cosine t squared. That is the second order derivative. Okay, that is about this section. Now, new section of our lecture notes. In fact, in your lecture notes now, this was very long section, which started 2 lectures ago. And this section is called mean value theorems. So, section 22.3, the mean value theorems. There are 3 of them, and but we start with the definition of local maxima and minima. So, definition. The function y equals to f of x has a local minima at x0 if there exists delta greater than 0 such that for all x in x0 minus delta, x0 plus delta, f of x greater or equal f of x0. Analogously, we can define local maxima. So, x0 local maxima if we have minimum, local minimum, minima, it's plural, maximum. Points of local minima, but one is local minimum. So, local maximum if there exists delta greater than 0 such that for all x, x0 minus delta, x0 plus delta, we have f of x less or equal f of x naught. And we have strict local maximum and minimum, or relative maximum and minimum, if the inequality is strict for x not equals to x naught. So for punctured neighborhood, the inequality should be strict inequality. That's it. So now theorem 1 here, Therma Rule. If y equals to f of x is differentiable at x naught and has a local minimum maximum at x naught, then f prime at x naught equals to 0. Proof. Proof. By contradiction. By contradiction. Suppose f prime, let's say greater than 0, not equals to 0. So let's say greater than 0. So what is f prime? F prime at x naught is limit as x tends to x naught, f of x minus f of x naught over x minus x naught. And it is positive, as we know. Then it follows by properties of limit there exists delta greater than 0 such that for all x from x naught minus delta x naught plus delta, except for the point x naught itself, of course, for all x from a punctured neighborhood, we have the function is positive as well. So if the limit is positive, then the function is positive. And then what it means, what follows from here. So first, for x greater than x naught, so x from x naught plus delta, what we know? X minus x naught is positive, hence we have f of x minus f of x naught is positive. And if x is from x naught minus delta up to x naught, then x minus x naught is negative, hence the numerator should be negative as well. And what those inequalities which mean for minimum and maximum? So we have f of x greater than f of x naught in every right hand side neighborhood, right neighborhood, and f of x is smaller than f of x naught in the left neighborhood. It means doesn't matter which small neighborhood of x naught we consider. The values of the function f of x will be either greater to the right or smaller than f of x naught. And it means that we cannot have at x naught either minimum or maximum. Contradiction. And the theorem is proved. Okay? So now next theorem, theorem 2, that is the first mean value theorem, which is called Rule theorem. Rule theorem. So if f is continuous on closed segment AB, differentiable on open interval AB, and f of A equals to f of B, then there exists C in AB such that f prime at C equals to 0. Proof. Proof. F is continuous on a closed interval AB. Hence, by Weierstrass theorem, f has a maximum and minimum. So m equals to maximum f of x and AB, and m equals to minimum exist. So both maximum and minimum exist, and both are attained at some points of the closed segment AB. Okay, of course, in general, minimum less or equal than maximum, right? Firstly, let us consider the case m small equals to capital M. What happens then? Let us think. Minimum equals to maximum. We deduce that f of x is identically constant, right? This is a constant, right? And then f prime at x equals to 0 for all x in AB. So arbitrary point is suitable for us in this case, right? So second case. Second case. M is smaller than capital M. So we know f of A equals to f of B, right? Let us consider values, the following values. So f of A equals to f of B f of a equals to f of b is between m small and capital M. And we know that the left-hand side and the right-hand side are different. Hence, at least one of those two inequalities is strict. Both cannot be equalities, right? Simultaneously. So at least one is strict. Without loss of generality, we can suppose, let's say, f of a equals to f of b strictly less than capital M, right? And capital M is still attained at a point, so let it be C in AB, in the interval, right? Because by Weierstrass we know that value of maximum is attained at a point of the interval. Now, what we have? Now we have the following. So, f is differentiable at C, right? And if we consider the following interval for all x in the interval C minus minimum of C minus A B minus C, and same we add, same value we add. So what we have then? Look, I consider AB, right? I have a point here, so minimum is this one. This one, B minus C is minimum, right? So that is the interval. So for all x from that interval, what we have? F of x less or equal than f of C, because of f of C equals to maximum. But then it means that this delta, this is delta greater than 0, this delta greater than 0, is precisely the delta from the definition of the local maximum. So it means C, i.e. C is a local maximum. Wait a minute. Local maximum point or local maximum? This abbreviation is not good, right? So has a local minimum at x naught, at x naught, at x naught, at x naught. We have local maximum at x naught. So, i.e. at C, f has a local maximum. Right? F has a local maximum at C, right? So, differentiable and has a local maximum. So, by Fermat's rule, Theorem 1 says then f prime at C equals to 0. That's it. That's it. And, okay, there are illustrations of that theorem, geometric interpretation, but we didn't consider yet geometric interpretation of derivative. That's it. A little bit strange. Okay, maybe I'll refer to what we studied in school. So the derivative is just a tangent, although we didn't define yet what means tangent. So if we refer to knowledge from school, then we can find the following geometric interpretation. Look. So we have a function, and if the values of a function are equal at the ends, then for sure there is a point somewhere where the tangent is horizontal, right? That is the sense of Rule theorem. Okay. Now counter examples. Example 1. Counter examples. To Theorem 2. Look at Rule theorem. We have three conditions: continuity on a segment, differentiability on an interval, and f of a equals to f of b. Three conditions. All three conditions, each of them is necessary. And now, count examples. So, firstly, forget about the very first. So, suppose it's differentiable on an interval, f of a equals to f of b. So, for that reason, let it be f of x equals to, let's say, x from 0 to 1, and 0 for x equals to 1. So the function is as follows: 0, 1, 1, and the graph is the following, like that, right? So the function is differentiable on an open interval, right? The values at the ends of the interval are equal, but definitely there is no point where derivative is 0. Why? Because the function is not continuous on the closed interval. We have no continuity at 1, right? Second, so let it be continuous now, but not differentiable. Very simple example: f of x modulo x, x from -1 to 1. So it means now I'll create the following graph, draw the following picture. Now we have modulo x. The function is continuous on segment -1, 1. The values at the ends are equal, but there is no point where derivative is 0. Why? Because the function is not differentiable on an interval -1, 1. It is not differentiable at 0. Just one point where it is not differentiable, and it disturbs the conclusion of the theorem, right? And the third one, okay, here I can consider just the closed interval doesn't matter, -1, 1 or 0, 1 doesn't matter, right? So here we have continuity, differentiability, but the values at the endpoints are different, and no point where derivative is 0. Okay. Next mean value theorem is Lagrange theorem, and most probably, yeah, I will be able to prove it. Theorem 2, oh, 3, Lagrange. Mean value theorem. If y equals to f of x is continuous on AB, differentiable on an interval AB, then there exists C in the interval AB such that f of b minus f of a equals to f prime at c times b minus a. Okay, proof. For the proof, consider the following function. Consider capital F of x equals to f of small f of x minus f of b minus f of a over b minus a times, let's say, x minus a. And we consider that function on the segment AB, that is well-defined function. So this is a linear function, and linear function is certainly continuous and differentiable everywhere on the real line. So the function capital F of x inherits all properties of the function f of x. So it is also continuous on the segment AB and differentiable on the interval AB. Moreover, what is about f of a? If we substitute x equals to a, here we have 0, that is f of a. And what is about capital F at b? It will be f of b minus f of b minus f of a over b minus a times b minus a And if we substitute, so we substitute x equals to b, then b minus a we cancel, so f of b is cancelled, and once again we have f of a. So capital F has equal values at the ends of the interval. Hence, by Rolle theorem, theorem 2, there exists C in an interval where f prime at C equals to 0. And what is capital F prime? What is it? Look, this is precisely what we want to prove. Because capital F prime is small f prime of C minus derivative of linear function is just the coefficient. And that is precisely what we wanted to prove. So what is geometric interpretation of Lagrange mean value theorem? It's quite analogous to Rolle. So look, now we have no restriction to values, to the values of our function f at the endpoints. So we have something like that, right? And then what is this f of b minus f of a over b minus a? This is tangent for the linear function which has values, same values at the endpoints as our function. So this is linear function. This is linear function. Yeah, in fact, its equation is y equals to this. So in fact, capital F, what is capital F? Capital F is precisely the difference between f of x and this linear function. Okay, shifted to 0, right? Slightly shifted. That gives, yeah, shifted to this one. This one. That is capital F. But it is not so important for geometric interpretation. For geometric interpretation, what is important? What is point C? That is a point where the tangent to the graph of our function is parallel to this line, which the question is about capital F of b. How is capital F of b equals to f of a? As it is written. Look, b minus a we cancel. F of b we cancel. So what remains? F of a. Is it clear? Okay. So that is geometric interpretation once again. So look, compare with Rolle. For Rolle, we have, I erased. For Rolle, we have horizontal tangent somewhere if the function has equal values at the ends, right? Horizontal, and now look, horizontal line is precisely parallel to the line which connects endpoints of our graph, right? So here we have a tangent which is parallel to the line which connects endpoints of the graph. That is geometric interpretation of the Lagrange mean value theorem. So Rolle theorem is a corollary of the Lagrange theorem. Although we proved Lagrange with the help of Rolle, right? So that is the connection between those two theorems. Okay, that's all for today. Good luck for midterm. Okay. Could you wait? Well.